Alright, so we're going to go ahead and do number 25 here. It gives us the graph not of the function f, but of its derivative. So that's what I go ahead and I'm kind of drawing that here. And it wants to know the inflection points. And remember, inflection points are places where the derivative, or where the slope kind of changes, okay? So, say we were given a function that looked something like this down here, and remember the function graphed in blue is the derivative, and say I were to graph like an actual function, and I have something like this here, then the inflection points are when the slope changes from increasing to decreasing, okay? So kind of like all along right here down in this other that thing that I drew, right in there you can see the slope is pretty steep. It's a negative slope and it's pretty steep, and then right about here the slope starts shallowing out, and you can see it starts shallowing out to this kind of this crest here. And so this point in blue, and I'll actually just do it in red, I'll cover it up in red, this point in red is called an inflection point. And again, that's when the slope changes from continuing to either increase and then starting to decrease. So in here, I'll kind of do it in green. Here the slope is pretty steady and it's pretty steep, and then it starts to level out. And so this point right here would be an inflection point. And so when we're given the graph of the derivative, remember now this is the graph of all the different slopes. So when the derivative graph or the slopes start to change, that's where we have inflection points, because the slope went from positive here and then started to decrease, okay? So I have this table over here, and it's like the second derivative. If we had a graph of the second derivative and it was something like this, and the second derivative was just a graph like that, then at this point here where the second derivative changes from negative to positive, that would be an inflection point. And so looking at the first derivative, that is when things go from either increasing to decreasing, like right here, or from decreasing to increasing, like right here. Okay? Alright, so that's how we find the inflection points on a graph given the derivative. Okay, now let's go ahead and do number 31. Okay. So number 31, we have this table here, and so I start kind of filling out all the values that are in the table, and it says estimate the x coordinates of critical points of let's see, all of the critical points of f from 0 to 10, and that's what we have this table here. And remember, critical points are when the derivative, and we have the derivative here, when the derivative is equal to 0. So these little pink arrows that I'm drawing in here, you can see that the derivative equals 0 somewhere in between these points here, because we go from 1 to negative 2, and in order to get from 1 to negative 2, we must have crossed 0 at some point, okay? And so I draw like a rough graph of this here, and I'm just going along and doing 0 is up here at 5, and then 1, 2 is kind of like right here, and I think I draw all this out. So you can see that the critical points, or where the slope equals 0, are kind of at all of these circled points on the graph here. And again, that's where it equals 0, where the slope or the derivative equals 0. This is the graph of the derivative, and it crosses the 0 line here, so that's when y is equal to 0. So that looks to be right about at 2.5, and at, let's see, what do we have here? 6.5, and then right about at 9.5, okay? So we have like 2.5, then we have like 6.5, and we have like 9.5. So those would be all of our like estimated critical points. And so we need to see if each one is a local min or a local max, and we know that this derivative goes from basically from a positive to negative back to positive, so we know that this is a max here, and this is a min here, and then this is a max here, okay? And again, that's because the slope is going from being positive here to being negative, back up to being positive above the x-axis. And so if you picture a slope being positive to positive, then that's like a slope going positive to positive, okay? And if we do that, then we can see that we have a max, and then a min, and then another max. And so that's exactly what we have here. All right, moving on to number 33, I believe. So number 33 is kind of, it can be confusing. It's if water's flowing at a constant rate into the container marked 4.16. So basically the bottom of this container is kind of shallow. Let's kind of draw the container here. And then it just goes straight up from there, and that's not the best drawing in the world, but it'll do. So we have this container full of liquid. And so when we're putting stuff into this container when it's empty, it's going to start kind of growing quickly, and then not as quick, and then once we get to here, it starts growing at a steady pace. It'll grow the exact same pace all the way up. So if we think about that in terms of slope, okay, or in terms of the function, we're basically saying that, let me switch colors here, we're basically saying that it's increasing quickly, and then starts to kind of level out here, and then goes at a constant pace after that, right? So down here, if we're pouring water in, water is rising quickly because it's a more narrow kind of passageway here, and then the height starts getting less, like starts growing less quickly because we're widening out. And so that's kind of what we're representing here, is we have, you know, this steep growth here, and then it starts to level out, and then right when we get to this point is kind of like this point right here, and everything starts to grow at a constant rate here, so we don't have like this big growth of slope, so it's just constant. Okay. All right. So number 35. Number 35, we want to find and classify the critical points of this here. So I'm just using the power rule really quickly. Okay. I take the derivative of the first, and that's what this is, times the second, plus derivative of the second times the first. And I just kind of do that quickly here. So then we'll want to go ahead and set that equal to 0, and kind of just do what we've been doing all along here. Set equal to 0 and solve, and that'll give us our critical points, and then we can go ahead and see if they're a maximum or minimum by seeing what the slope is doing on values on either side of those critical points. Alright,